Okay, so today we discuss modified Euler's method. It's also called as Hume's method. So the idea is to use the formula from Euler's method to obtain a first approximation to the solution y at xn plus 1. So what is the idea of modified Euler method? Is to use Euler's method to obtain the first approximation to the solution at xn plus 1. This approximation is denoted by y star n plus 1 so that it can be written as y star n plus 1 is equal to yn plus h f of xn yn. N is equal to 0, 1, 2 and so on. So this approximation is improved by applying Euler's method once again. But this time we use average of slopes of the solution curve through xn yn and xn plus 1 yn plus 1 star. Okay, so what is the difference? In Euler method, we use tangent lines to approximate analytical solution, but in modified Euler's method, we use average of slopes of the solution curve through the points xn yn, xn plus 1 and yn plus 1 star. So for example, if n is equal to 1, so this point will be x1, y1, and the next point will be x1, x2, and y2 star. So y2 star will be computed by Euler's method. So this gives yn plus 1 is equal to yn plus, so here we can replace 1 by 2h f of x and yn plus f of xn plus 1 yn plus 1 star. So modified Euler's method or modified Euler's approximation can be interpreted as arising from first stepping to the point. Okay, so it's a, you can say it's a rising curve or rising graph, so which is going towards the point P. So how we can compute P is the x coordinate is xn plus h by 2 and the y coordinate is yn plus h f of xn yn over 2 along the tangent line to the solution curve through x and yn, and then stepping from P, this point, towards xn plus 1 and yn plus 1 along the line through P whose slope is f of xn yn star. Thus the modified Euler's method for approximating the solution to the initial value problem. So here we can write dy by dx, or derivative of y is equal to the function of x and y, where the initial condition y at x naught is equal to y naught for n is equal to 0, 1, 2, so on. At the points xn plus 1 is equal to x naught plus nh. So is can be written as yn plus 1 is equal to yn plus 1 by 2h f of xn yn plus f of xn plus 1 yn plus 1 star. Where, so this yn plus 1 star can be written as yn plus h f of xn yn for n is equal to 0, 1, 2. So this is the Euler's formula. We can solve a question by applying the modified Euler's method as with the step size 0.1 to approximate the solution at x is equal to 0 of the initial value problem as given below. So here at x is equal to 0, the value of y is 1 by 2 and the function is f of x is equal to y minus x. So because the function is of two variable, we can also write as f of xy is equal to y minus x and step size is 0.1. So we compute first yn plus 1 star is equal to yn plus hf of x and yn, and yn plus 1 is equal to yn plus half h f of x and yn plus f of xn plus 1 yn plus 1 star. So this equation will take the form yn plus 0.5 h yn minus xn. So there are some mistakes. So we are correcting these mistakes and will be shown later. So plus yn plus 0.1. So this should be the value of this 1 by 2 is equal to, here should be 0.5. Okay. So then f of xn yn is yn minus xn. So this value can be obtained from this function. So f of r, you can say that this can easily evaluate from this value, you see. So since f of xy is equal to y minus x, so f of xn yn is equal to yn minus xn. So later this we can replace with, you see here, so yn minus xn. So similarly, f of x n plus 1 and yn plus 1. So f of x n plus 1, we can again go back to here. Okay, so we can write this yn plus 1, okay, minus yn plus 1 star, and we will get these values. Okay, then after simplification, so we will have a generalized form, and this generalized form we will use step by step. For example, for n is equal to 0, we will have y1 is equal to y naught plus 0.5, 0.05 into 2.1, y naught minus 1.1, x naught minus x1. So here you can replace the values. X naught is equal to 0, okay, and the first step 0.1 can be used as x1, okay, and then 2.1 y naught 0.5, because at x is equal to 0 the value is 1 by 2. So then we have simplified in the form 0.5475. Similarly, for n is equal to 1, we have calculated this value. For n is equal to 2, 4, 5, 6, 7, 8, 9. Okay. So after 9 iteration, so we have the solution at y is equal to 1 plus 0 equal to 0.5579. So next method is Runge Kutta method. So it's a German names. For example, these methods are an important family of iterative methods for the approximation of solutions of ordinary differential equations, and were developed around 1900 by the German mathematician Carl David Ptolemy Runge and Martin Wilhelm Kutta. So in English we can say Carl David Ptolemy Runge and Martin Wilhelm Kutta. But in the German, we can say Carl David Ptolemy Runge and Martin Wilhelm Kutta. RK4 or classical Runge Kutta method or Runge Kutta method of order 4 is the most popular member of the family. So RK4 is one of the most powerful predictor corrector algorithms of all, one which is so accurate that most computer packages designed to find numerical solution For differential occasions, we'll use it by default. The fourth order Runge Kutta method of approximating the solution of the initial value problem is, so this is the initial value problem, and the points can be written as xn plus 1 is equal to x naught plus nh. So what is the Runge Kutta method? Is a simple formula. Yn plus 1 is equal to yn plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4, where for n is equal to 0, 1, 2, 3, n minus 1, this k1 can be evaluated as directly hf of x and yn, and k2 can be evaluated as hf of xn plus half h yn plus half k1, and k3 can be evaluated as hf xn plus half h yn plus half k2, and k4 can be evaluated as hf of xn plus 1 yn plus k3. So this, if we apply to solve the problems, so it's not so difficult. Apply RK4 with h is equal to 0.1 to determine an approximation to the initial value problem below at x is equal to 1. So dy by dx is equal to f of xy equal to y minus x, where y naught is equal to 1 by 2. So for n is equal to 0, if we compute k1, we will have the value 0.05, and for k2 we have the value 0.0475, for k3 so 0.047375, and for k4 hf of x1 y naught plus k3 0.1 into 0.547375 minus this point is equal to 0.04473, and y1, so here we can obtain the first approximation. So y1 is equal to y naught plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. So y1 is equal to 0.5 plus 0.047424037 equal this value. Similarly, for n is equal to 1, x1 is equal to 0.1, and y1 is equal to 0.547424007. So k1 again can be calculated as k1 is equal to hf of x1 y1 is equal to 0.1 0.547424004 minus 0.1, so it will be equal to 0.0447, and k2 can be calculated as hf of x1 plus half h, so y1 plus half k1 is equal to 0.1 0.5698 minus 0.15, we will have this 0.042, and k3 can be calculated as hf of x1 plus half h y1 plus half k2 is equal to 0.1 into 0.5684 minus this equal to 0.0418, and similarly for k4 we have this hf of x2 y1 plus k3 is equal to 0.1 to 0.5892 minus 0.2 is equal to 0.0389. So here we calculate y2 is equal to y1 plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4, and this y2 is equal to 0.547 42404 plus 0.041688 equal to 0.5893. Similarly, for n2, we can calculate the values taking x2 is equal to 0.2 and y2 is equal to 0.5893. 893. And so K1 will be modified to 0.0389 and K2 will be calculated as 0.0359. K3 can be calculated as HF of x2 plus half h y2 plus half k2 is equal to 0.1, 0.6073 minus 0.25 equal to 0.0357. K4 is equal to h f of x3 y2 plus k3 is equal to 0.1, 0.6250 minus 0.3 equal to 0.0325. And this substituting these values in the formula, we will have y2 plus 1. So it should be, here is y2 and y2 plus 1 equal to y3. So y3 is equal to 0.625, and then we will compute y4 by replacing n is equal to 3. So for replacing n is equal to 3, we have x3 is equal to 0.3 and y3 is equal to 0.6251. So again, in the similar way, we need to calculate the value of k1, which is equal to hf of x3, y3